All right, what goes on Y?
Pressure.
All right, what does it look like?
A Y.
I have the toolbox up. I don't want the toolbox. I want the colors. That either. Stamps. Have people put it there. There we go. All right, what does it look like?
A Y.
Looks like a Y. My ladies over there need to stop talking or separate.
Solid, liquid, and gas.
All right, solid, liquid, and gas. What's over here?
Solid.
What's in the middle?
Liquid.
And what's in the middle?
Gas.
All right,
And then the dot in like the middle right here.
it's called the what?
Triple.
All right, what's the triple point mean?
That it like connects them all.
All right, that's not what I'd ask you about if it was a quiz. So what does it mean if I ask you about it on the quiz? Solids, liquids, and what happens if the solids, liquids, and gas? Shh, Emma, shh. Solids, liquids, and gases do what?
They all,
Those of you who are talking, stop. I understand that you were out yesterday. Right now, while I'm talking, is not the time to try to get what you need. Solids, liquids, and gases do what at that point?
All exist.
All exist at equilibrium. All right? All right. Did everybody get that? Solids, liquids, and gases exist at equilibrium. Now, what's the next point we need to know? All right. The dot at the top is the what? The critical point. What happens at that point?
That's the highest.
All right. Shh, Bryce. I get that. What did I just say? Now is not the time to try to catch up people who were absent. Okay?
Yeah.
That's the point at which what can no longer exist? The liquid. At that point, once you pass that, you're a what? You're a gas. All right, so there's two more points that we have to label. What are the last 2 points? All right, the boiling point and the melting point. Where do we find those? Okay, what do I have to draw in first, though? Where's the line have to be at? All right, well, how do you know it's 1/8? What's that? There, standard. There you go. So you said ATM, but that's based on what the pressure is labeled as. Now, if it didn't say didn't say ATM, it said torr, what would you put it at? If it said KPA, you'd put it at. All right. So in this case, since you said ATM, I'll make it 1 there. So you're going to have to draw in a line. Some graphs may have it, but if it doesn't, you have to draw it in. All right. So Bryce said where it intersected the solid liquid line, that would be the what point? The normal melting point. What's the same as the melting point? Normal freezing point. All right. And this will be the what point? Normal boiling point. All right. Question 2. What conditions are needed for a liquid to boil? Something about atmospheric pressure. What conditions are needed for a liquid to boil?
Heat.
Oh,
Sarah Ellie said.
Sarah Ellie did say it yesterday.
When the atmosphere needs
No,
it's the equilibrium. No, she said pressure. Vapor pressure.
What about equilibrium vapor pressure? Yeah, we did talk about it yesterday. At least y'all remember that part.
Atmospheric pressure.
What?
Equilibrium vapor pressure.
When equilibrium vapor pressure equals what?
Atmospheric pressure.
Yes. When equilibrium vapor pressure equals atmospheric pressure. A liquid does not boil until those two things are equal. So today, what can you tell me about looking out the door?
It's foggy.
It's a little foggy, but at the moment, the sun's coming out. So pressure is going what? Up or down? Up. So the boiling point is going to do what? Go up. Where would the boiling point of water be the highest? At the coast. All right. Why? It's closest to sea level. It has higher pressure at the coast. All right. How would we find the normal boiling point on an equilibrium vapor pressure graph? Those of you who are not here, quit saying I don't know. I know you don't know. It was on YouTube last night. I am fairly certain that you didn't watch it, okay? I'm aware that you don't know. The only difference is I just don't care. So stop saying you don't know. I don't care, okay? Nor do any of your classmates. They might lie to you and say they do, but they don't either. With the exception of the 4 people who had an AP exam, I don't know why the rest of you were not here, and I don't care about that either. Just shut up. So, if you have an equilibrium vapor pressure graph, how do you find the normal boiling point? Standard pressure, all right? Just like with the phase diagram, you have to find standard pressure. So let's say this one's in torr, just to change it up from the first one we drew. So what's standard pressure in torr? All right, so let's say we find 760 to be along about this range. So what do we need to do, Jennifer? Draw a line. All right, so from there, what do I do, Rebecca? Find the point, and then I read where? Yep, and find the temperature. Any questions? All right, let's talk about homework and see if you have any questions. Those of you who were not here yesterday, we did the back side of the graph that we had earlier in the week with a staircase. Oh, okay. You didn't want to do it like Fort Hill did, where you wrote all over it in multiple colors so it's hard to read?
No. I don't feel the need to do that unless you'd like me to do. Try to make it simple.
I have a question.
You need one of each of these.
I have a question.
What?
I wasn't here Monday when we turned in open engineering. You didn't tell me.
Put it up there on my desk.
I did that once.
All right, so if you have homework and would like to go over it, get it out. It was that was the back side that we did, and you need one of each of these I just set on my desk. Yeah. That's what I'm getting ready to do if I can find it. So I don't have to read all 29 questions. There it is. All right, so question 1 is C. 2 is C. 3 is B. 4 is C. 5 is D. 6 is B. 7 is A. 8 is D. 9 is C. 10 A. 11 is C. And 12 is D. Questions about anything on that page?
No.
So we did well on that page? We got the answers right? We felt good about those?
No, I don't.
Okay. All right, number 13. B. 14 is A. 15 is B. 16 is A. 17 is D. 18 is B. 19 is A. 20 is C. 21 is D. 22 is A. Questions on that page? Huh?
Is this stuff in the benchmark?
These exact questions?
You know, but like,
The content, yes. It's also on the next test, which will be next week. Probably Friday. 23 is B. 24 is B. 25 is C. 26 is B. 27 is A. 28 is D. And 29 is A. Questions on any of those? Anybody have a question? Something you didn't understand? Want to ask about?
what is glycerol? What is glycerol?
Oh, glycerol, it's just a liquid. It's just a liquid that you can compare to water. Question about that one? So if it says glycerol boils at a higher temperature than water, what does that tell you about its attractive forces? If the water temperature for water is lower, if it boils lower than glycerol, what does that say about the strength that water holds its bonds together versus glycerol? It's going to be weaker. Water will be weaker. Glycerol's attractive forces will be stronger. Huh? Yeah. So yesterday, when we looked at the equilibrium vapor pressure graph, we had 3 graphs. We had A here, we had like B here, and we had like C out here. And I asked them which one had the strongest attractive forces. All right. And C had the strongest attractive forces because it had the highest boiling point, right? So if in the question it says glycerol has a higher boiling point than water, what does that tell you about glycerol's attractive forces? They're going to be what? Stronger than water's attractive forces. So anybody who has a higher boiling point will have higher or stronger attractive forces. Okay, typically waters are pretty strong, but there are some liquids that have stronger attractive forces than waters. And in this case, this question is leading you to believe that glycerols are stronger. Okay? Anybody else? Question? Anything on the homework? No? What of them? That one did in class. So somebody who was here will be glad to show you those answers. All right, if you will, those people who are here need to separate like Selma and Betsabe so we can do our quiz. The rest of you will have a different quiz, and it's a makeup quiz. It is not the same. It's longer and has more questions on it. What? Yep, 2 different quizzes this time. So, if you will, Jennifer, Eric, Juliana, Alicia, Sarah, Ellie, Bryce, Rebecca, Betsabe, Salma, and I think that's it. Y'all need to put your stuff away so you can do your quiz. I don't think there's any math on here. There isn't, so you don't need a calculator. All you need is your brain cells.
So what is that? What is that on? It's on this stuff?
This plus yesterday and a little bit from the day before. It's up to you. I give it to you. I think I have enough copies. I'll make one real quick.
The little card, bro. Is it on the stuff?
Put your homework up, Russ. You might have to go make another copy anyways. He's trying to hand you yours. You taking it? 'Cause if you are, I gotta go make a copy because I got that space in my hand. Okay. You cannot sit directly across from Bryce.
Oh.
And I assume the rest of you did not want the papers from yesterday.
Wait.
The ones I sat here and said, if you wanted them, come get them. Papers that we used yesterday. Gabriel Trench. It's got to be this general pressure. It has to be there. This will be. What?
Bring that line just in, bad.
73. I return to quiet. What does? Maybe you're still working on the quiz. You got a couple? All right. Anybody now? Who's still working at this point? Anybody? Simon, are you working or are you done? Because I can't tell. No more, okay. You done? All right, if you will, several here, pass up the paper. Get out here and go around. Just pick a spot there, not there. All right, so did my 9 who took the quiz notice anything about where 6 of those questions came from? Came from the homework paper. So if you did the homework and you actually paid attention to the answers, you ought to have 6 of them right because they were typed directly from your homework. All right, which is why the other people have a different quiz because I'm not giving them a quiz where they already know where the questions come from with the answers. All right, so try doing your homework sometime. So you might have benefited, Tevin, to have taken it if you actually did the homework. I know, but I wasn't going to tell you that up front. All right, so if we go back to where we were yesterday, so find your notes. If you weren't here, it's your job to catch up. All right, we did 2 graphs yesterday. We're doing a 3rd one today. The test will be next week. All of the information that we did yesterday has a high chance of being on the exam at the end of the year. Destiny, I need you to get off your phone and put it away. I need Hyro to take his earbuds out again.
Is the fifth one to take next week, the last one?
The one you take next week will be your last test of the quarter, yes.
And then the final.
Yes, it will not be your last grade of the quarter, no, but it will be the last test, yes. Okay, because I will grade almost to the end. All right, so yesterday, we were talking about connects. And for those of you who are not here, this is a little bit of a review for you, just to get us up to speed with where we're going today. All right, what were the 5 factors that can make a reaction go faster? Now, we said in order for a reaction to go faster, we need molecules to do what? We need them to move faster, and the reason we need them to move faster is so they can do what more often? Collide, okay? We need molecules to collide. Now, why do we need them to collide? All right? Why do we need them to collide? Anybody remember? In order for reactions to be successful, what 2 things had to happen? All right, all reactions have to have proper orientation. And the way I explained this yesterday for those people who are here is if you go to plug in a plug, might only have 2 prongs, and you go to plug it in the outlet, every time you plug it in, does it line up correctly and go in? No, sometimes prongs have that longer prong and the shorter prong. And when you go to plug it in, you have to flip it so that it'll go in right. Have any of you ever plugged in a 3-prong plug and you got to plug it in? It's got a round and then 2 flat ends, and you've got to plug it in, and you've got to plug it in, you've got to rotate it so that it'll go into the 3 holes. Yes, if you plug it in and you've got the round lined up with the flat, is it going to go in the hole? No, molecules work the same way. If they hit and they don't hit in the correct orientation, they are not going to react. All right, what was the second thing they had to have? Enough energy, okay? Now, I'm going to change that word to sufficient. Instead of saying enough, we're going to say sufficient energy. All right, and I gave that a name that we're going to use today. Anybody remember the name we wrote down in parentheses? Activation energy. We're going to talk about that here in a little while. Okay, activation energy. So we need molecules to collide. The more collisions they have, the better chance they have of having the right orientation and having enough energy. So we want them to collide a whole lot, because out of 1 million collisions, they might only have 1,000 that are successful. That's not many collisions that are successful when you talk about bumping into somebody 1 million times and you only have 1,000 successful collisions. So you want them to collide as often as possible. So how can we get them to collide as often as possible so these 2 things can happen? What 5 things do we say we could do? You only have your phone. All right, we said we could. All right, for those people who are not here, the 5 things we said we could do, and I'm not writing everything down, that we did yesterday. You get the notes from somebody or watch YouTube. We said we could increase the temperature. If we increase the temperature, what do the molecules do? They move faster. If they move faster, they're going to bump more often, and they're going to do it with more what? More energy. All right, what's the second thing we could do? We could increase the surface area. If we increase the surface area, there's more exposed area. One of the examples we talked about yesterday was, how many of you have used granulated sugar versus cube sugar? If you use cube sugar in coffee, a lot of people like to use cube sugar with tea if they serve it to people, because it's much neater to pick up cube sugar to put in something than granulated. If people have to scoop granulated sugar into a cup, what happens? It spills all over the place. It makes a mess. But cube sugar, it's nice and dainty. Pick up a little block, stick it in your tea. You don't make much of a mess with that if you're serving it to people. But granulated sugar, you usually get sugar all over the table, or if you're serving it like in a living room setting, people generally just make a mess. And if you're a neat freak, do you want sugar all over your floor or your table? No, it gets sticky. All right, it gets in the carpet. It's a mess. So people like to use that, but it has less surface area. So if you have a cube like this, the water can only attack the outsides of the cube. But if you have a whole bunch of little itty bitty pieces floating around inside the sugar, and this pen does not do dots very well. All right, all of those outside pieces of the sugar, the water can attack those outside pieces. So there's more surface area to be able to dissolve. All right, what was the third thing we said? Concentration. For those of you who are not here, this is a new vocabulary word. Concentration is the number of particles. So if we increase the number of particles, we increase the chances of collisions. Sort of like right now. If you run up and down the main hall, are you going to bump into anybody? I would hope not. I mean, there's a problem if you bump into anybody at 10:30 on the main hall. But if I made you wait until 11:40 when everybody who's a freshman is trying to go to lunch and everybody else is changing classes, can you run up and down the main hall? Well, you can, but you're going to do what? You're going to bump into a whole bunch of people. Bryce. Yep. All right, number 4. What was the last one that you knew yesterday? Add a catalyst. A catalyst's sole function is to speed up a reaction. Y'all talked about that in biology class. Probably talked about enzymes, maybe with digestion. If we don't have enzymes in our stomach after we eat, we tend to feel how? Sick and bloated. We need it to speed up digestion so we don't feel terrible. All And the last one we talked about was the nature of reactants. Some things just react faster than others. So I asked you for some examples. Give me something on the periodic table that's pretty fast, Salma. Anything that you can think of that's fast. Pick a group that would be fast. Group 1 would be fast. Can you give me another group, Hema, that would be fast? All right, group 2 would be pretty fast. Lil, give me another group that you think would be fast. We're 3 weeks from the exam, and I don't know. Brian, can you give me another group that you think would be fast? Group 1, group 2, and
18.
17.
thank you, Hyro. All right, very good. All right, group 17 is what I was hoping for there. Group 1 and group 17 are the two most reactive groups on the periodic table because they're how many electrons away from 8? 1. Group 2 is pretty reactive, and you could even argue group 16. But group 1 and group 17 are the two I was shooting for that would be the fastest. Who is not going to be reactive at all on the periodic table? Group 18. They have 8 electrons. They're not going to react, so they shouldn't even be part of the conversation. All right, who would be pretty slow up there on the periodic table in terms of I'm not going to react fast at all? Give me one, Destiny. A section that you would say, nope, not going to be fast, Ms. Wall. Huh? I don't know. Bryce, give me somebody up there who's not going to be fast. D-block, be a great example. Can you give me one more, Tevin? F would be fine. That was what I was shooting for, but F would certainly be fine. Can you give me one, Eric? Well, or a group.
I say group.
14 would be fine. Okay, they're sort of middle of the road. All right, just stay away from groups 1 and 2 and over there towards 17. Anywhere in the middle part of the periodic table is going to be fine. All right, D, F. F is never going to be part of the test. All right. Now, from there, how do we represent these things that you guys just showed and talked about? All right, this is the part I stopped at yesterday because Betsy May was like, Ms. Wall, we need some practice. And I hope that when I grade those quizzes today, that I'm pleasantly pleased with the answers y'all put down because you actually did the practice and you got the right answers. Somehow I have a feeling I'm going to be disappointed. But that just tells me you didn't do the homework that you asked for. Now, a potential energy diagram. You're going to have to be able to read these. I would almost bet that you will see one of these on your exam somewhere. I don't have much money, so I'm not going to bet money. But I would be stunned speechless if you did not see one of these on your exam in the 45 questions somewhere. Now, over here on the y-axis, you will see something about potential energy or energy. I have no way of knowing how it will be labeled because I never get to see the exam. The x-axis will say something about a reaction. Now, this can be labeled in multiple ways. They can write an actual reaction. They can write just something generic like course of the reaction. They might write something like A plus B yields C. It could be some made up reaction. It could be almost anything down there, but it will have something about a reaction on the x-axis. Hyro. Draw 2 of these because they're opposites from one another, and you need to be able to read both. Now, this is one of them. Now, there are 2 things you have to be able to find, and you need to be able to read them in the forward and in the reverse direction. Now, the first thing we need to be able to find is the activation energy that we've been referring to. We said in order for a reaction to occur, we need to have some minimum amount of energy, some sufficient energy to get this reaction going. You can't work if you don't have proper orientation and you don't have sufficient energy, right? So, activation energy. So what is it? Everybody got what they need? All right. First of all, activation energy, because I'm tired of writing this word out. Is abbreviated E with a little a. Capital E is the universal symbol for energy. And we put a little a there to remind you that it's activation energy. Now, this is the minimum energy to start a reaction. Now, how are we going to find this? Now, the nice part is it is always found the exact same way. It is from the reactants to the top of the curve. It's from the reactants to the top of the curve. It never changes. Okay? Never ever changes. Are you caught up with me? All right, so we go back to the graph. If this is a reaction, where are the reactants always at in the reaction? First or last? First. They're the beginning, right? So if this is a graph, the reactants are always at the beginning. The products are always at the end. So on any activation or on any potential energy diagram, the reactants are always first, the products are always at the end. So when we want to find activation energy, all right, activation energy is from the reactants to the top of the curve. That is activation energy. Now, the reason I drew that line there is right now we're just labeling. When we practice this in a minute, the graphs I'm going to give you have numbers on them. Okay? So let's just say for a moment that this was at 40 and this was at 60. What would the activation energy be? It would be what? It would be 20. Because the reactant started at 40 to the top of the curve is 60, the activation energy would be 60 minus 40, which would be 20, and the unit would be kilojoules per mole. And it's labeled on the graph we're going to do. So I'm not going to clutter this up in a second. Now, we have to do something else with activation energy. So let me cruise back over here. All right, you also have to find EA with that. This is called activation energy. Let me say this, reverse activation energy. Let me write it that way. Reverse activation energy. Okay, reverse activation energy. Now, that's EA with a accent mark. Now, if I'm reversing the reaction, where would I start at to reverse it? That's right. So this will be from the products to where?
Top of the curve.
To the top of the curve. Okay, from the reactants to the top of the curve. From the products, because you're reversing it. So where do you start if you reverse the reaction?
No, that's just earlier you said from the reactants.
Oh, sorry, from the products. I meant products. I'm getting old. Hey, at least today I didn't come in and tell you I forgot to teach something yesterday. I did that the last 2 days. from the products. All right, does everybody have it? So if we go back to our graph, all right, where do the products start? Down here at the bottom, right? So let's say that this number is at negative 20. Okay? So this time we're going from here all the way up to here to find EA reverse. Okay? All the way to the top of the curve. So EA reverse would be what? All right, so we put a little 0 in right here.
Would it be 80?
All right, it would be 80. Now, so you're going from negative 20 to 0, which is how far? That's 20. And then you're going from 0 to 60, which is what? So you're actually going 60 plus 20, which is 80. Is everybody okay with how we got that?
No. Wait.
All right, Salma, this is a number line in math class. All right, on the number line, where are the products at? They're down here at what number? Negative 20, and we're going from negative 20 all the way to what? 60. So from negative 20 all the way to 60, how many actual numbers are we crossing from negative 20 to 60? We're crossing 80. That's why the number is 80 for EA reverse. Does that make sense? Okay. Everybody with me? All right. The most important thing on the graph you have to be able to find, which goes with our last topic that we'll probably wind up working with today, that'll drive y'all cuckoo. All right, is delta H. Delta H is called enthalpy. Enthalpy is heat content. Now, you remember when we talked about Q and I told you there wouldn't be any negative numbers and we'd get to negative numbers at the end of the year? We're there. All right, delta H is where we get positive and negative numbers. Q never gets positive and negative numbers. We only do that with delta H. All right, delta H, if it's negative, tells us it's an exothermic reaction, which you should remember means heat is what? What happens to the heat if it's exothermic? It's released. Good. How does it feel to the touch, just as reviewed, since we have a benchmark coming up? How does it feel to the touch? We're supposed to have taken one yesterday. No, today's second period. Feels hot. Okay. Delta H, if it's positive, then is endothermic. So here, heat is what if it's endo? It's absorbed. And it feels how to the touch? Feels cold. We did this way back the first week of school. I gave you baking soda and vinegar. You mixed it together, and it got cold in the bag. All right, so we need to figure out in our graph, is it endo or exothermic? And we need to calculate delta H. So, how are we going to find delta H? Any ideas?
You subtract EA and reverse EA, something like that.
Nope, don't have to do EA. Where on the graph to where on the graph?
Oh, from like the top to the bottom.
All right, what top to what bottom?
Reaction.
There you go. Okay. Delta H is found from the reactants to the products. All right, delta H is from the reactants to the products. Now, the only difference between EA reverse, or delta H reverse and delta H without the accent mark is whether it's positive or negative. It's the only difference. So, now we just need to read our graph. Everybody got it? Can I turn the page? All right, so if we look here, not there, here, can you tell me, first of all, whether this graph is endo or exothermic? In looking at it, most of the time I usually get 2 or 3 people who can tell me whether it's endo or exothermic.
Excellent.
All right, I hear an endo and I hear an exo. Tell me why you think it's endo. Okay. Tell me why you think it's exo.
So we're all the way down because it's energy.
Okay. Why'd y'all say it was exo over there?
Then going down.
Wait a second, going down.
Okay. So look at where they have the right answer. All right, look at where the reactants are and look at where the products are. All right. What happened over the course of the reaction? The reactants are here and the products are there. What did the products do? Did they absorb energy or did they release energy? They released. Whoops. All right. The products are lower, which tells us energy is released. Okay. So that tells us this is exothermic. So the 3 or 4 people who said exo because the products are lower were correct. Now, the products would be where? The products would be higher. So the reactants will be down here and the products will be up here. It'll be flipped. It'll be like that. Now, what does that tell us about our delta H for this graph? What does that tell us about our delta H then for this graph? Delta H has to be what? You just told me that delta H was what? You just told me it was an exothermic graph, so it has to be what? It's got to be a negative delta H. Okay? So, Salma said delta H was found by going from where to where? Where'd she say it went from, Salma? Reactants to the products. So I'm going from here to where? To here. So I'm going from here to here. That's my delta H. And you just told me it was what because it was exothermic? It's negative. Now all we need is the number that goes with it. Where do the reactants start at? 40. Where do the products end at? So we've got 40 and we've got 20. So it's negative 60. Now, delta H reverse. The only difference is we're going the other direction.
Isn't it just going to be positive?
That's exactly right, Salma. The only difference is we're starting here and ending here. So the direction of the reaction is we're not exo now, but we are endo. So the numbers are the same, except that it is positive 60. That is the only difference in delta H. Are you with me or no? Yes or no? Yes or no? You're sure? You were talking to Hyro. Destiny, you with me or not? Are you sure? If I had a quiz on this tomorrow, could you do it? You will see one. Yes, tomorrow.
I can do it. So what's the question gonna look like?
Like I'm going to give you a graph and ask you to label activation energy. I'm going to ask you to find delta H. I'm going to give you a graph and ask you what the parts are. All right. First of all, what kind of graph is it? How do you know it's endo? All right. We should know this is endo because the reactants are here and the products are there. All right. So for those of you who are not as quick as Brian, the products are higher. For those of you who don't understand that, I don't know what to tell you short of I'd memorize it. If the products are higher, it's endothermic. Okay, we're at the end. It's crunch time. Some of y'all's grades just suck. You're going to see this graph tomorrow. You're going to see it on the exam. Whether they ask you endo or exothermic, I don't know. I would assume you're going to see something about activation energy, something about a catalyst, or something about endo or exothermic. I'm going to talk about a catalyst in a minute. I'd learn endo and exothermic. If the products are higher, it's endo. If the products are lower, it's exo. I'd memorize that. Okay? If 50% of your overall grade, is it too late to pass my class? No. It's really hard to fail these days if you've got a 10-point scale and 50% of your final grade is an exam. In case y'all don't know math, it's really hard to flunk the class. Really hard. All you got to do is put a little effort here in the last few weeks, study for the exam or show up for the reviews. It's not hard. It's not even too hard to pass with a decent grade. Now, are you with me on its endo? Can you do that tomorrow if I ask you that question? Because you will see a question that asks you if it's endo or exo. Okay. So how do I do activation energy? Where does activation energy start? If we cruise back to the notes, activation energy starts where? From reactants to the where? Top of the curve. This is where a little studying comes in handy for those of us who won't do that. So, to my graph, where are the reactants at? Right here. Everybody got that? To the top of the curve. So, let's just say that this time, my number's at 0 for the reactants, and it's at 100 this time. So what's my activation energy? It'd be 100. Okay? Huh? They're not all going to have negative numbers. We're not at delta H yet. We're not at delta H yet. Okay? So activation energy in this case would be 100.
So there is no difference.
And I need to make my product something. Let's make them 60. All right. My EA reverse. All right. EA reverse starts at where if I do EA reverse, Hiro? If I cruise back to my notes, EA reverse has to start where? And go to where? So, my products are here. And I'm going to the top of the curve. So my products start at what number? And I go to the top of the curve. So what's my EA reverse? 40. You with me on that? Are we okay on EA and EA reverse? Yo, Hiro. You were the one who said you didn't get it. Are we okay on that? Yes. All right. So delta H. How do we find delta H? We need delta H and delta H reverse. All right, Destiny, how do we find delta H? Where's it come from? What's that one and that one? All right, so from the where to the where. Give me the right words. No. No. The R and the reactants and the products. All right. So where are my reactants at? 0. Where the product's at? So if I subtract from my 0 to my 60, I get what? 60. So I know my delta H's are both 60s. The only question is, are they positive or negative? So what can you tell me about this reaction? Is delta H endo or exothermic? What is it, Emma? So was endo positive or negative? So that means my delta H is positive. That means my reverse is what? Is negative. Are we okay on that? Before we practice. Because now I'm going to give you something to do. Can what? You've had a snack. It was called grab and go. Yeah, Miss Fire was something. Alright. I want you to do the 2 graphs on the front. Find me the answers. You're finding for both graphs EA reverse, delta H, and delta H reverse. Those are the things you're finding in both graphs. Kevin, shush. Find some answers. What?
Could you go back to the one we did earlier?
Mm-hmm. What is what? Delta H is enthalpy, heat content. You put down what? Yeah, that's how you find it. So you change, or you go from the difference from the reactant to the product. Anybody have a question?
Yep.
That would be from negative 150 to 0, we go from negative, or from 0 to 100 to 250. EAs are not negative people. EA is not negative.
Oh,
You come check.
EA is a positive number. The only thing that's going to be negative is delta H.
Well, I'm not here.
Because you're going from negative 150 to 0 and then 100, from 0 to 100.
It's negative, but it's 100, but.
So what? So that's negative 150 to 0, and then from 0 to 100.
Triangle eight.
And don't estimate, they're on whole numbers, okay? Don't try to estimate that it's close to 100, it's just a 100. No. You're at negative 150. That's it. So you're going from negative 150 up to 0, and from 0 all the way up to 100. That's 250.
So the reverse.
That would be the reverse key.
Okay, I'm done.
You need a calculator?
Yeah.
Slow. I feel like I'm slow.
Damn.
You see what I did?
Where? That one's at 150. Yeah, it's at 150. Put it at 150. Yeah. EA 100, then negative, or just 250. That would change that to from 0 to, so that would be negative 150, and then the reverse would be positive 50.
Miss Wall, I need your help because I don't know how to work this out.
You don't know how to do what?
I don't know how to do this.
Okay, Delta H reverse, what is it?
Yeah, so use 150 still.
Yeah,
works.
So it's
Yeah, it's 0, and it goes to. Use that as.
I just put 150. Look on it. Look on that.
Is this reaction right here endothermic? It's endothermic. This delta H is positive 50, reverse is negative.
I know what it was.
You just got her back. This is endothermic. It's not like, delta H is positive. That's negative.
all right. So now.
This is the number line. From here, all the way up to there. So you're at 150 to 0, so that's 150. Then you go from 0 to 100, so that's another 100. So that's a total of how much? You're just adding the numbers together. You're going from negative 150, or all the way from down here on the number line. You're at 150, going to 0, so that's how much? And you're going from 0 to 100, so it's.
No, you're, okay, do, okay,
We don't know what's right.
you know how to do it.
For Delta H.
Like, show everyone do that.
Sure how to do it.
Delta H.
And then
For the second one.
Okay, you're subtracting. I'm not doing, I'm not subtracting or adding, I'm just moving on a number line from negative 150 all the way to 100. How many spaces are you moving on the number line?
Okay, look. From
Yeah. Yes. 250.
See,
That's the answer?
Yes, 250. That's what I'm getting ready to go over. You're just trying to answer the questions.
So you're taking it, you're taking it.
No, you're trying to just move from here to here for reverse activation energy. And here to here. So you're doing activation energy. You're going from here to
I mean, it doesn't.
You're going from here all the way up to there. On number line.
No.
Negative 150. And then you're going from zero.
Oh, the video's going to
Plus 100 is. All right, let's talk about these. Some people are having a hard time. Some of y'all have got it cold.
I'm just a little confused because you got like different numbers for your delta H. And I didn't.
No. So those of you who are talking, A, stop. So I can explain. And those of you who've got it, try to pay attention just to make sure your answers are correct. Now, I realize these graphs look a little funky, and so you're trying to estimate. But this, just assume it's 100. Just assume this is at the 150. Stop trying to estimate and change it to, it looks like 140. It looks like it's like 90, okay? Just assume that they're at 100 and 150. Now, when you do EA, EA is here, you're going to the top. So you're going from where to where? EA is from 0 to 100. So if you do this, you're going from 0 all the way up to 100. Now, some of you are trying to calculate like 100 minus 0 and calculate that way. You can do it that way, and there's nothing wrong with it, and that's fine. The problem you're having, though, is when you get to EA reverse, and then you're getting hung up with the negative numbers. So my advice to you is stop that, all right? Look at your numbers. You're going from 150, and you've got a 0, and you're going to 100. Because you're going from here all the way up to here, right? So everybody's okay with where we're going to. That's not the hard part. You're getting hung up with these numbers over here. You're going from 150 to where? 0. So you know you've already got 150. And then you're going from 0 to 100. So you're going 250 spots on the number line. Stop worrying about the negative signs. EAs are not negative, okay? You're crossing 0 on the number line. So you're at negative 150. You're going to 0. That's 150 spots on a number line. And then you're going from 0 to 100. So you're going another 100 spots on the number line. So you want how many places on the number line? 250 places on the number line. So the unit that you get is what? What's the unit on the number line? KJ per mole. So KJ per mole. Now, when you do delta H, there you have to worry about your signs because those are positive and negative. Delta or EA is not. So we're at the reactants, which are at what? 0. The products are at negative 150. So 0 minus 150 is 150, isn't it? So 0 minus 150 is 150. Now, is this reaction? All right, Bryce. They said send you. All right, so finish the back side. If you've got 0 to minus 150, is this endo or exothermic? It's exothermic. So if it's exothermic, make it negative. The delta H that's reverse, it is endo in the reverse, so make it positive. Now, for the second one, EA goes from where? From 0 to where? To 80. So EA is 80. EA reverse goes from the products to where? So the products need to be estimated at what number? 50. So 50 to the top. So 50 to 80 is how much difference? 30. Delta H goes from the reactants to the products, which is 0 to 50, which is 50. Now, delta H reverse is also going to be 50. So the only thing we need to figure out is this graph endo or is this graph exo? It's endo, so that means delta H is positive. So delta H reverse is negative. Does that help at all? All right, I want you to do the back side. Right now. No, right now. Y'all won't do it for homework. Do it right now. And then we're going to move on and talk about entropy. No. We got to talk about a catalyst on the graph in a minute. But do those three real quick.
No.
Situations. Okay, well,
Find me the answers quickly.
Are you gonna go over these?
I am in a few minutes. I'm just waiting on you to have time. If you have a question, ask me. I'll be glad to come help you. I'm just giving you a chance to get started. Anybody stuck? Need help? Yeah. All right, we got time? Yay? Have you done at least two?
Yeah.
Okay.
No.
No.
All
If you've done at least two, I'm fine. All right, so EA for the top one, you go from -20 to 80. So what's your EA? 100. Oops, I can't look up at the board and write. EA reverse, you start at looks like about 60 and you go to 80. So EA reverse is 20. Delta H to delta H reverse looks like we go from what? 60 to negative 20 is 80. So is this an endo or exothermic graph? It's endo, so positive, and then reverse will be negative. All of the units should be kilojoules per mole all the way down. Everybody got it? All of them should be kilojoules per mole. Anybody not get it? Need me to redo it? Come on. You started at what? You did it at 40? Huh? Okay. I can tell you the ones on the quiz are a little more obvious than this one is.
I did 48.
But otherwise, you're okay? Come back. All right. So for the second one, did you use 0 and negative 40? The second one. All right. So for the second one, EA, we have 0 and negative 40. How about negative 20 on, or 20 on the top one? We're okay on 20 on the top one? All right, so EA, we got 0 to 20, so EA is 20. EA reverse, we have negative 40 to 20, so we have 60. All right, kilojoules per mole on both of those. Delta H, we have what? Negative 40 to 0, so that's going to be 40. So delta H reverse is going to be 40. Is it endo or exo? So we said it was negative and positive. Yes? All right, so for this one, EA reverse, delta H, and delta H reverse. All right, so did we say 70, 0, and 10? So that's at 70, and that's at 10, and this one's at 0. Are we okay with those numbers? All right, so we went from 0 to 70. So that's 70. This started at 10 and went to 70. So that's 60. Yes? All right. So for delta H, we went from 0 to 10.
Yep.
So is it endo or exothermic?
Endo.
All right. I hear endo. All right. So positive and negative. And they're all kilojoules per mole. Yes? No? Anybody need me to go back and explain? Anybody? So if I ask you to do any of this tomorrow on the quiz, we can label the parts. What's activation energy? Energy needed to do what? To start the reaction. It's the sufficient amount of energy. We okay with those words? Yeah. What two requirements are needed to get a reaction going? What are the two requirements? Proper orientation and sufficient energy. What are the 5 factors?
Concentration.
Increase surface area.
Reactants,
So everything we did today is some of the
Surface area, nature of reactants, area.
Okay. If you don't know, when do you need to know it by?
tomorrow.
All right. So we need to talk about a catalyst now. All right. So before I forget, because I'll forget if I go much longer, because I've been trying to keep it in my brain. I've already missed something 2 days this week. Let's not do it again. All right. So how does a catalyst affect a reaction? We're getting there. If I add a catalyst, how, oops, let me change color a little more. Not quite that much. How is it going to change my potential energy diagram? What's going to happen to it? Any ideas? All right, it's going to speed it up. So how's it going to change in that diagram? If it's going to speed it up, what's it going to do? So what's it going to do to the diagram? If it speeds it up,
It's gonna flip it.
what's it going to flip?
reactions in the product.
The product. The reaction.
Oh, is it on the like really straight down? So it comes out like that? Yeah, there you go.
Remember, reactants and the products are going to stay in the same place. All right. All it does is it lowers the activation energy. Okay. It lowers the let's not S off there. All right. It lowers the activation energy. It makes it easier to start the reaction. Okay. How does a catalyst affect a reaction? It lowers the activation energy and it makes it easier to start the reaction. Now, if it makes it easier to start the reaction, it makes it faster. Okay? Generally speaking, if it's easier to get y'all out of the bed in the morning, you're going to be what? Faster getting ready. If it's harder to get out of the bed in the morning, you're generally what? You're grumpy, yes, but you're also what? You're slower to get done what you need to do. Okay? Reactions are the same way. Questions? Anybody? All right. Tomorrow we're going to talk a little bit about how reactions can occur and why some reactions occur and why some reactions don't occur. In order to do that, we have to learn about entropy. And yesterday on your worksheet, I gave you another word for the word entropy. So we're going to talk about entropy to finish out today. And entropy is pretty easy. It's an easy way to end the day. Does everybody have what they need off the board? Kevin, put your phone up. All right, I didn't hear any no's out there. So, entropy. Anybody remember what I told you to put down for the word entropy? Entropy is disorder. Okay? Entropy is disorder. Now, just like enthalpy, it also has a symbol. It is delta S. Okay? It is given the symbol delta S. So, we're going to look at this in a couple different ways. First of all, when you talk about a solid, a liquid, and a gas, based on those, who would have the most disorder or now the most entropy? That's right. All right. A gas will have the most entropy. And who would have the least entropy? That's right. So we could actually do greater than and less than signs, but I won't do that at the moment. Now, we can also use this same concept to look at chemical equations and talk about whether entropy is increasing or decreasing. So let's look at something like that. Okay? Make sure I'm not skipping anything like I did the other week. Actually, this week. Let's see here. Yep, we did that. We did that. We did that. Got all that. Did the catalyst. Good, good, good. All right, we're going to do that tomorrow. Yeah, we did that. No, we cannot chill. There is no chill because we're not even going to finish the curriculum. Okay. Yep, we're doing fine. The swallow is on point. I haven't skipped anything we need to skip or I meant to do. Yeah, we're in good shape. All right, so what's happening there? Is entropy increasing or decreasing? What do you think?
Decrease.
Why do you say increasing?
You said gas is at the top, then liquids are behind.
Okay, so tell me what you said again. Maybe I misunderstood you. What'd you say was happening to entropy?
Well, let's say that gas is going to liquid.
Okay, so is it increasing or decreasing?
Decreasing.
I heard decreasing there. What'd you say?
Decreasing.
Decreasing.
You
All right.
said increasing.
He said increasing at first. I thought he did. That's why I was like, maybe I misunderstood. Because I thought I was losing my mind. Thank you, because I was just thinking I'm nuts. You know, I am getting old, and I'm thinking I'm getting senile in my old age. But thank you. It makes me feel a little better, Liliana, because I thought I was losing my mind. You know, I'm feeling my blood sugar's dipping a little bit here, and I'm thinking maybe I need to eat my banana between classes. But shoo, I'm not nuts. Thank you. All right, so is it increasing or decreasing? So how do we decide? What do we look at? All right. Brian was right when he said he looked at the states. It was a solid, it was a gas, it was a liquid. All right, we got a gas here, and we have a liquid here. That's exactly what we want to look at. That's very good. So gas changes into a liquid. Perfect. Now, if we go from a gas into a liquid, what is happening to our disorder? It's decreasing. It's going down. Okay? Delta S is decreasing. Okay? Delta S is decreasing because you're going from a gas into a liquid. Are you with me on that? Okay. So, what if I had one where I had let's do all right, I gotta write the symbols legibly. Like this. What would that be?
Increasing.
Okay, why do you say increasing?
Because you're changing from the solid to gas.
All right, that would be increasing. That's good.
Because what?
You change from a solid to a gas. Even though you have a solid on one side and you have this solid on that side, it's still changing from a solid. Changing from a solid into a gas. So that's why they said increasing. Okay? Now, what if we have
On that graph?
like that? What if I have this?
It stays the same.
It's decreasing.
It's decreasing, yeah, I see.
Wow.
Because there's soap in a sink. All right, what if we have that?
Decreasing.
All right, I hear decreasing. And I heard stays the same over there. Really? You're going to take the dish soap and not the hand soap? I mean, there is hand soap. I mean, you use the dish soap, but there's hand soap. All right. So how do we decide?
Don't know.
All right. The first thing you need to check is the what? Check the states. What do the states tell you? They're all what? They're all gases. So that's why Salma said they stay the same. But I had a few people over there that said decrease. So why'd they say decrease? All right, so how many coefficients are on this side?
The right side or the left side?
The left side. I thought y'all were child prodigies for a minute, and I was so impressed.
Well, there's two that one is a 1 and a 3.
That's right. So there's how many?
Four.
Wait, what? Wait, what's your?
You took what exam yesterday?
Calculus.
And you just told me there's a 1 and the 3, and there's how many?
Well, I thought you meant how, like.
You thought I meant what? There's how many over here?
Four.
There's 4, and since we're in a chemistry class, can we use the right term? There's how many what over here?
Four code word.
What do we call those things if there's 4 what over here? Starts with an M.
Numbers.
Moles.
Oh.
4 moles. Okay. So there's 4 moles over here, and there'd be how many on this side? You know, those old packups are looking so much better to me at the end of this year. All right, so we got 4 moles on this side and 2 moles on that side. So is my entropy increasing or decreasing? Is decreasing. So my delta S is decreasing. Okay, I told you entropy is pretty easy. It's a good way to end the day because it's an easy concept. Okay, you with me? Okay. Now, let's practice that. And then we'll be done for today. Now, don't lose. No, never mind. I put it on separate paper. So I don't have to yell at you if you lose it. All right, all you got to figure out is whether the examples are increasing or decreasing.
So we're having a chill day tomorrow, right?
No, there's no children. We're going to take a quiz. We're going to talk about gifts. And we're going to move on to chemical equilibrium.
When are we gonna do lab?
Well, entropy? Very possibly, yeah. Yeah. You were washing your hands. It's on YouTube.
I'm gonna go eat it now.
An idea or eight?
You might have to tell Howard he was washing his hands. All right. So on the line, all I want you to do is tell me if it was increasing or decreasing. So look at the equation and decide if entropy is increasing or decreasing. And there might be a couple where it doesn't change or stays the same. I am. Because I'm still not convinced my blood sugar's going to drop to 12. Even though Brian was changing his answers on me.
No, well, I said
There's an
decrease
easier
both
way.
times.
Go to the bottom.
Tom was changing. Huh?
Really easy. Go to
Decrease, right? That's a decrease. And then you said decrease too.
When it's harder than I do at the bottom.
When it's hard.
Oh, I'm so proud of you. You had to?
Miss Wall.
You have to drink the coffee?
Miss Wall.
Okay.
Do you have a Band-Aid?
Not for you.
Warm coffee. Like dark coffee.
And she doesn't like chewing gum.
Should keep the thing on.
You always have better gum.
You said cute, and I put including method.
That's for her labs.
Here's a glass.
Solid.
And I mean, it's Miss Wall. So this one good as that?
Oh my gosh, Miss Wall.
Yes. Just you got my phone.
I told you to come here.
Oh,
Hey, what?
I hear you. I really want to that. Right, oh, cool.
Okay, no. 14. I need one for water.
Because those are all cash. Now, if you're
So smart.
1.3. Yeah, 4 on the side, 2 on that side. So if you were babysitting 4 kids and you go down to 2
Hey,
kids,
we're
Tell
going
it to her, let's see what it's like.
decrease. That's right.
I'm gonna be it.
But like here, that's a liquid size. You know,
It
if
stays the same.
you go from liquid
Yeah,
to
like,
solid,
literally
increase
just
or decrease.
Even the most.
Decrease. That's what you're getting.
Is that what you got for,
Like solid to gas. That increase or decrease.
decrease?
You got a lot of things to do.
because you know how to say. I got increasing all gas.
Whoa,
You have to oh, sure.
that's an eight. They look tricky.
On 7 and 8.
Miss Milwaukee, come here.
I thought.
7 goes from aqueous. Where does aqueous fit? I didn't even think about aqueous.
Liquid.
It fits between where? If we cruise and we look at
Liquid and a gas.
And that's why I think
Liquid is-
solid,
forgetting things.
I know, liquid and gas, aqueous goes, that looks terrible. AQ goes there.
I was right.
Really?
So what is, what?
Increasing the- oh, yeah.
A liquid's gonna have more order than aqueous. Because aqueous has got stuff dissolved in the water. So it's gonna be, I guess I should draw the other way, because more order, a gas is gonna be more entropy. So let me draw my greater than signs that way. That'll be more, that'll be less. That way. Your homework is to study for your what? Study for your quiz. I thought you were working on a project.
Oh.
I didn't bring that one. I'm sorry. You brought it.
As soon as the bill
You did some brutal stuff.
Oh, I forgot to take my glasses
My parents know it too. They raised the complainer.
That's all right. I'm raising 2 more.
Complain.
I'm
You got you all dressed up. Why are you dressed up?
I was like, man, he was like, and I'll be judging you when you.
My glasses gonna be bad.
You don't have a job, you might learn all, go more class.
Nuh-uh.
You were late.
I'm not scared. That's the thing.
Be able to- I can hold it sometimes. You know, when I was little, I would pee all over me. That's why they switched out the clothes that we had.